we are actually using martensite. The pure martensitic, we cannot use it, impossible. Now we know that we have different kinds of phases, bainite, pearlite. Ferrite is the most soft, pearlite little bit harder, bainite even little bit harder, martensite even little bit harder. So if I would combine some of these phases together, I would get the benefit of both of them. That's what is a dual phase material. You are combining ferrite and martensite. It means basically you are having ferrite, but at the same time some austenite is getting converted to martensite. It means I am getting higher elongation, higher strength, or a higher yield point and higher elongation. Maybe the strength is not that high as martensite, but still I am getting that same energy. My aim is to get this required energy available in whichever ways. So dual phase steel that we had studied DP600, DP700, DP800, ferrite, martensite. Now people say, Arey, I don't only have ferrite and martensite. I also have bainite, pearlite, even carbides. Why not mix it? Yes, that's exactly complex phase material, CPW material. It is basically pearlite in bainite with some retained austenite and some retained martensite. So now what we are doing it, increasing again the strength, and basically your pearlite is giving you that deformation, plus you have some retained austenite. We don't want to convert that. That is again added by some silicon manganese, and we are getting that formability. So CPW materials, complex phase material. Now people thought, why I always have to use the temperature to increase the martensite strength? Is it not possible to avoid this temperature completely? Yes, and that's how the steel started emerging, trip steel or a twin steel. What is that steel? Austenite, but by deformation, that austenite converts to martensite. Transformation induced plasticity or twinning induced plasticity. So basically what we are doing it, instead of temperature, we are giving mechanical force to convert that into that. Finally we are getting martensite structure, but it is not 100% martensite because some kind of austenite will remain. That's why we are getting also high deformation possible. So trip steel comes to very closer to what we are showing now here, that is high strength plus at the same time high elongation. So you see that banana diagram is very logical. If we know this three styles of metallurgy, we know everything, that we need to change the crystal structure, which is feasible. We need to add some alloys. Example, why alloys is creating some hardness? People told today bake hardening. What is bake hardening? You add some nitrogen inside your crystal. So what is happening? The elements will not able to glide easily because there is some kind of resistance coming from the alloys. Small alloy, carbon, nitrogen. But then you give some energy in terms of heat, and then it can be formable. So basically you are creating strength by giving 180 to 200 degrees centigrade, which you call bake hardening. So bake hardening is nothing else but alloy steel, a low alloy steel where you use the alloys like nitrogen and carbon. Now people tell, okay, what is high alloy steel then? You know that this structure, this is pure iron. Let's remove one iron and put chromium or vanadium, molybdenum. Automatically you realize that structure is getting damaged. Structure is getting deformed. The slip cannot happen so easily. It means the strength increases. This we call it as a high strength steel. So basically you see the logic is very simple. You have to create resistance to the deformation. You automatically create the high strength. But at the same time, your resistance should not be there that it can create crack. Otherwise the purpose is not solved. It should go much and much endlessly. So, as I told you, the initial, let's go back something 100 years back. It was only iron was allowed. No one knew about the steel. Iron is nothing but IF steel. Pure ferrite structure, nothing else. Interstitial free steel means no interstitial means no carbon. practically ferrite structure. A very good deformable material, though not that high as austenite, but quite good because no resistance to the slip. That's why you have this 180 to 260 strength, but not much useful because you will be somewhere, the energy is less. Good for the outer body parts, but no more use for the structural parts. Then came the bake hardening steel, as I told you, putting nitrogen first, carbon, mainly nitrogen. And they realized that this nitrogen basically goes inside the crystal structure when you give the temperature. That's how the word bake hardening. So the first hardened steel which came into picture was bake hardened steel. And when do you give temperature? You deform the part, you send it for the painting, and there is a chlorine temperature of 180 degrees centigrade, and that is sufficient for the nitrogen to move inside the crystals. And that's how the strength is created. So the second one, bake hardening steel, you get around little bit more, 300 megapascal of yield strength. Little bit more we got it, that's it. Then came microalloy. Microalloy, here actually it means that we are adding small alloys, mainly the carbon, increasing the carbon content from say 0.1 of ferrite to go to 0.7. It means practically it is a pearlite. So what is we are calling is microalloy is actually a pearlite structure. Then came here this basically trip steel. Trip steel is the first steel where you start thinking of completely phase transformation in terms of martensite, but by giving the deformation. Dual phase steel, here now the temperature started coming in picture. Why temperature started coming in the picture? Because your retained austenite is converted to martensite, but even the ferrite is kept in the picture. So we are controlling the temperature such that you produce ferrite as well as martensite. So first time the temperature came into the picture, obviously temperature in terms of austenite, and then going back down in terms of DP material, dual phase material. Then came the complex phase material and found the martensitic steel. Now this is a typical banana diagram. So I wanted to tell you that what you see in banana diagram is nothing illogical. Even we would have done the same thing if we would 100 years back, and if we would know the steel structure, that we would need to increase the strength, we would need to increase the elongation, and we know who is making the strength and who is making the elongation, right? So this is about the dual phase steel. You basically here in this area, you hit it faster, but quench it faster, but then you go slowly so that you have both ferrite as well as martensitic. You normally get around 500 to 600 MPa and quite good formability. Trip steel or twip steel, transformation induced plasticity or twinning induced plasticity. Like this is a twinning. Normally we have a higher elongation because here we have a not ferrite but austenite, retained austenite and martensite structure. Austenite, as we know, it is a very good formable material. Better as austenite, nothing exists. Unfortunately, we are not living at 700 degrees centigrade, else I wouldn't have got necessary of any steel, I would have only used austenite. High strength, high formability, everything very good. So DP 500, DP 600, trip, again more formability, CPW little bit less, and finally you can see the martensitic very less, but going at very high thing. So this is very small background. It has nothing to do with my lightweight, but wanted to give you idea that we will be learning in the similar frame. We will be making our own processes. Now, basically, we have got the material. Let's see what automobile is doing with these materials, how they are basically making parts from that material. The first and the most important thing is to use the high strength material. As we know, when you take high strength material, it is very difficult to deform. Very, very difficult to control the feasibility of that. It cracks, it gets wrinkles, it has high spring back, it has high press force, the tool wear is extremely high. So many OEMs, including our OEM, thought of the first approach to use the warm forming. The warm forming is mostly used by majority of OEM, and that we also call it as press hardening steel. Warm forming, as I told you, is very simple. You go into the austenite phase. Austenite phase begins at 723 degrees centigrade at eutectoid point. But we are not working at eutectoid point. We are working little bit lower than eutectoid point. So you have to increase the temperature, and we normally go to 950 degrees centigrade. At that temperature, practically everything turns to austenite. Means everything has FCC structure. Now this structure is very good, deformable structure. You can give a complex part and everything, and then you cool that thing faster or intentionally slower. It could be. Basically we are not just cooling it, we are cooling intentionally. Some area faster, some area lower. So keeping martensite, bainite, pearlite wherever we want. And that's what actually is the crux of the press hardening material. The press hardening material is available in, basically I am taking the example, UZ board material. UZ board is a basically material coming from ArcelorMittal. Every company has its own thing. And the main reason here is 22MnB5. The name could be irrelevant. Boron 5%, manganese 22%. And this constituent is very, very important for the press hardening material. Once you have this material, you can see that initial phase, before it is in delivered stage, when it is not yet formed, you have basically quite good formability, around 10%. The strength is also not that high, 500, 700. So original material is quite soft to handle. But then after deformation and after producing your final strength, you can see the difference between the yield strength. You go up to 1100, 3 times the strength. And that is what actually important. Plus, very important, in spite of this strength, you still have around 6% elongation to 10% elongation left in your thing. It means it cannot produce that fast cracks. You need some kind of area, plastic deformation. Otherwise, it is like a glass. It's a brittle glass. It will break up. And that's why this UZ board is a very good material, because it has some kind of ductility which prevents the brittleness. Maybe not that high as stainless steel or net dot has ferrite, but enough to prevent the brittleness. Otherwise, what will happen? Your car is going, it crashes, it absorbs the energy, and immediately it cracks. That is, the further energy will directly come to you, because the part has lost homogeneity. And that is the worst thing that can happen. So very important that this material has some kind of uniformity. This material has an added advantage that it has a coating on it. Normally what happens that if you raise it to 700 degrees centigrade and again cool it, your zinc coating will anyway not work. It will evaporate. If I don't give the coating, the steel will corrode. That's why there is a separate coating which is necessary, which you call aluminum silicon coating, and that is applied on this UZ board material. And this coating basically does not evaporate, it melts at this temperature and spreads uniformly throughout the part. And it remains on that. And this coating is important to give the corrosion protection to this steel. So now this banana diagram we have invented, we realized that we could maybe having the same thing if we would be in 1900. This is the material, press hardening material.